All right, everyone, and we are back, and we are going to go through some of the questions that are on our problem set and basically get our solutions. So let's read the first question. So read the following article and fill out the materials tetrahedron describing nanocrystalline metals, the impact of structure on and processing. So let's see if we can copy this, but if not, we're just going to go to our good old PDF here. Then we'll copy it here. And we need to figure out what are the steps on our materials tetrahedron. So let's see if we can copy. Nope. Let's see. Copy. Paste. There we go. So let's look at this article. Okay, so it's talking about, we can just read it from the abstract, nanocrystalline structure, grain size gets less than 10. And basically it's talking about there's several different processes that we can actually create. And actually you can see kind of this modeling, and we're looking at some of the values. And actually there's lots of processes that give us nanocrystalline materials. And you can actually see here, size of the crystalline, elastic moduli, and heterogeneous. Excellent. So, and actually experimentally show the relationship. All right, so we see that there is, as we create nanocrystalline materials, and actually we can go ahead and start to draw our materials tetrahedron. So our materials tetrahedron has basically what, where? Four corners, we're at the center with characterization. So we have properties, performance, structure, and we have process for our processing. So when we have a nanocrystalline metal, one of the ways you start off with your metallic material, and it has grains. Now, these grains are large in size, can be micrometers, can be millimeters, so they can vary quite wildly. So you could have basically nanocrystalline, so 1 times 10 to the minus 9, all the way up to 10 to the minus 3, so that's about 6 order of magnitude, so that is significant. So how do we decrease the size of these grains? You can do it in many ways. So one way could be mechanically. So you can you can cold roll these materials, and by mechanically deforming them plastically, you initiate essentially dislocation motion. You create smaller and smaller and smaller grains. You can also do several other processes depending on how you basically, do you cold forge the material? Do you hot forge the material? But anyways, so if we do a process like cold rolling or another kind of basically process, or basically any way we can kind of decrease the grain size or create dislocations, we can do this process of cold rolling to create nanocrystalline materials. Nanocrystalline materials have structures that are basically on the order of a nanometer. So this process, cold rolling, created this nanocrystalline structure. How does it change my properties? Well, mechanical properties, my yield strength increases. My strain at failure decreases. So I create a material that's more strong, but is also also more brittle. And how does that affect performance? Well, again, I've created a material now that's very, very, very strong, so it's not likely to plastically deform, but I've also created a material that's also more brittle, and it affects mechanical properties significantly. So that's one example of how you can fill out that materials tetrahedron. All right, on to the next one. So determine whether, actually, I'm going to zoom out quickly here, and then I am going to delete everything. Excellent. Classify whether statements are true or false. If false, correct the statement. So for Bragg diffraction, we only need a series of regular space obstacles. That is false. We also need what? We need a wavelength that's commensurate on the spacing between those regular space obstacles on the order of d. We also need constructive interference. Perfect constructive interference to get a signal. Metallic bonds can break and reform at room temperature. Nope. Those are what types of bonds? Intermolecular bonds, so van der Waals, H bonds, all those things. Metallic bonds are intramolecular interactions and have bond energies on the order greater than kT. I must utilize a wavelength on the order of an angstrom to investigate intermolecular spacings on the order of micrometers. Nope, that's too small. I need it to be micrometers if I want that type of spacing. So that's what I need there, so that is also false. Ionic bonds can reform at room temperature. Nope, we already said that. Intermolecular interactions have energy greater than 1 kT. Nope. They have energy on the order of kT, so that's also false. Destructive interference leads to no signal on the intensity versus 2 theta curve. That is correct. All right. Covalent bonds are intermolecular reactions with an energy of 100 kT intra. So intramolecular. Intramolecular reactions can break and reform at room temperature. Nope. We keep asking over and over. Ionic bonds share electrons. So remember, they do not. Those are covalent bonds. So covalent share electrons. Metallic bonding has delocalized valence electrons. Yep. Oxygen is an anion with a -6 charge. So it is an anion, but oxygen is going to be 2-. So van der Waals interactions are intramolecular and excuse me, and energies greater than kT. Nope, they are inter, and their energies less than kT. Excellent. All right, what type of bonding will be exhibited by Cr? Well, that's pretty straightforward. It is going to be metallic because it's a metal. What about CaCl2 and MgO? Peak is a polymer. Actually, we'll get to that in just a second. But let's go ahead and pull up periodic table. There we go. So to determine whether it's ionic or metallic, if it's ionic or covalent, or if it's some type of polar covalent interaction, we need to look at electronegativities. And we can see electronegativities on this handy, actually it's on the other side. Let's go look over here. Give us a second. So it's going to be on this. Electronegativity is on the second one here. So I think we have CaCl2. So let's go ahead and look at calcium. So electronegativity is let's look more. So it's the second one up. So calcium is 1. So let's go ahead and pull that up here. So Ca electronegativity is 1. What about Cl? Let's go to here. Let's go across the table, and let's actually go to another table. Where is our Cl? Where is our chlorine? There it is. Chlorine is 3.16. So Cl is equal to 3.16. So remember, I think that value is 1.7, I believe. So if we're greater than that, this is definitely an ionic interaction. What about Mg and O? So let's go ahead. O is 3.44. So let's go back here. O is 3.44. What about Mg? Let's go back here. Mg, where are you? You're on the difference page. Again, I don't think it's not the structure page. We need you here. And 1.31. 1 is Mg. So again, that will also be ionic as well. So ionic. We know ionic reactions either give or take electrons. They can, again, any intramolecular interaction cannot spontaneously break and reform at room temperature. For metallic bonding, they are delocalized electrons. And if we look at peak, so peak is an interesting polymer. Let's look at images. So you see these aromatic rings here. So these will have steric interactions. So big molecules like to repel one another. These are very stiff bonds. These oxygens lead for potential polar interactions and different types of peak, as you see here, the C double bond to O. So there's going to be a lot of polar interactions that are going on here, in addition to large, bulky steric interactions that are stiff. So those intermolecular interactions, they also have intramolecular covalent interactions there too. All those big bulky rings are carbon-carbon double bonds. So the steric interactions, the potential polar interactions, those are going to spontaneously break and reform at room temperature. All right, MgO, which is the cation, which is the anion? Mg is the cation. It is 2+, O is 2-. This is going to give up electrons, this is going to gain electrons. This will give up 2, this will gain 2. How about UO2? So U will be 4+, O 2-, and there'll be 2 of them. So this will give up 4, this will gain 2, and then the other one will also gain 2. What about Fe2O3? Fe is 3+, O is 2-, and there are 2 of these, 3 of these, and give up 3 electrons, gain 2, or this will eventually gain 2 electrons. And that's it. So there we are. So that's going to give those up, and those are anions, cations. So cation, cation, anion, anion, anion. So that's what we got. So these will always gain 2, gain 2, gain 2, give up, give up, give up. All right, finally, we looked at different potentials in the class. So one of the key potentials was our Lennard-Jones potential. So let's go ahead and start to calculate some of these values for us. Waiting for Mathematica to open up, but be patient. Mathematica is a great tool for us to use. We are very fortunate to have it. All right, so our ULJ, Lennard-Jones potential, is 4 times epsilon, just call it eps, times sig divided by r, basically to the 12th, minus sig divided by r to the 6th. And let's go ahead and plug that in. And then we're going to look at, we will get that ready to go in just a second here. Fantastic. So we're told in this problem also, we ran a simulation. So we said that EP was equal to 0.9 joules. Fantastic. Sig was 2.1 angstroms. So sig 2 is 2.1 times 10 to the minus 10. I need to use SI units. So that's my Lennard-Jones potential. What is the distance, what is the equilibrium distance between chromium atoms? So equilibrium distance is just when, again, we have the atom and atom are just touching. So in our Lennard-Jones potential, so ULJ, we always have here, here, and here. Here is our equilibrium distance, this R naught, and that's when the atoms are just touching. So when they're just touching, they are separated by a distance of 2r apart. We see that if we go to the left here, our energy increases. We are going to repel. We don't want to be next to one another. If we go to the right, we are going to attract. Because anytime I move closer here, my energy drops. So they want to attract. They want to come together. So, and this is our minimum. So that's when our first derivative is 0. We see that this is our inflection point. That will be when second derivative is equal to 0. So how do you determine the curvature of a function? That curvature is always the basically second derivative of ULJ with respect to r squared. And this is r, distance between the atoms. So let's look at chromium. Chromium, chromium, where art thou? Where art thou, chromium? All right, let's see. So chromium is a metal, so we want to look at the metallic radii, so the second one there. So where's my little chromium? Chromium is a BCC structure. We will learn more about that in a bit. Chromium, 1.3 angstroms. So my CR E naught, or CR R naught, is equal to 1.3, or actually 2 times 1.3 times 10 to the minus 10. So that's my R naught there. So that's the equilibrium distance for chromium atoms. What's the equilibrium distance from this potential? So the equilibrium distance will just be the derivative of ULJ with respect to R. And I want to solve, when is that equal to 0 in terms of R? And I want to get, let's just get the real values. Reals. And I want the positive because we can't have a negative distance. So this is my distance. What is the equilibrium distance? Got it. What distance is the force? So we know that the force is equal to minus derivative of ULJ with respect to R. So I also need to find when the derivative of force with respect to R, when is this equal to 0? And it should be at a larger distance. R reals. And that seems to compute, so fantastic. What is the force at a distance of 3 angstroms? So I could just do force slash dot R goes to 3 times 10 to the minus 10. And we see that that force is negative, makes sense, should be attractive. So they should attract one another. Fantastic. Excellent. Let's see, draw the locations there, explain our results. The force is negative, they should be attracting. The stiffness potential, and we're good to go. So this potential doesn't match, so something's wrong, but that's how it goes. Fantastic. That is your first piece set out of the way. So hopefully you did well. If not, better, we'll improve next time, and I'll see you in the next video for piece set 2 solutions. Thanks. Bye.